Hello, everyone. My name is Lan Jiang. Other co-authors are Clara and Nigel. I will represent them to present this work. Our work is synthetic dataset generation for fair and fairness research. So the motivation and the background of this study is currently machine learning models have been implemented in high stakes assessment and educational tools. For example, the essay scoring or personalized recommendation of the question or materials. And machine learning models tends to make biased predictions regarding demographic features because, for example, race or genders. The reason for that is uh, might be highly imbalanced data, or sometimes the model cannot capture some specific scenario, so they tend to use the demographic feature to make the predictions. Um, and currently, the fair educational AI are focusing on debiasing of the unfairness. So they're trying to remove those unfairness. However, they haven't tested their methods on all possible scenario because only limited data sets are available for evaluation. And based on only a few a few data sets, they only tested on a few unfairness conditions, given there are so many definition of the unfairness. So for this work, we aim to generate unfair data set with particular unfairness definitions. So we want to provide more benchmark data sets because currently those benchmark data sets may only show unfairness towards the specific unfairness definition, but they may not express show unfairness on other unfairness definitions. So we want to generate more data sets, and we want to consider more unfairness definition and provide more benchmarks. So we came up three research questions. The first one is, can genetic algorithm be modified to create a method for generating synthetic educational datasets that capture unfairness while still maintaining accuracy? The second one, we are caring about the generalizability of the methods we developed in the research question one. So we want to know for what kind of classification problems do data generated by genetic algorithm accurately capture unfairness? And also, does the difficulty of the problems affect the performance of this generation methods? For the third one, we want to know how do existing debiasing methods perform given generated unfairness benchmarks, and for which fairness definitions. So now I will start from the research question one. Can we use genetic algorithm and modified genetic algorithm to create unfair data sets? So the genetic algorithm is actually inspired by Darwin's theory of natural evolution. So this theory is trying to mimic the process of natural selection, where the fittest individuals will be selected for reproduction in order to produce offspring for next generation. The first step is the initialization in our work. So we want, the first step is trying to generate a population with different kinds of the genes. Then we're trying to, for those whole population, we want to give each data set a score. That score is the fitness of this data set. So this fitness evaluation is combined by the score of unfairness and the score of the similarity. So ideally, we want to increase the unfairness, but still keep the generated data set similar with the original data set, because we still want to maintain the relationship between the feature and the labels in the original data set. So given that we're, for each data set in this population, we're having a score, like fitness score for each data set. Like a higher fitness scores means that they have a higher probability of being selected. And the next step is selection. So we will select the fitter individuals for next population. So in our case, we're selecting fitter data sets, like a higher, like a data set with higher unfairness and higher similarity. So for example, in this case, we select those four data sets. And the next step is crossover. We will select a crossover point based like from those parents, and then we do the crossover. So that means we are swapped the feature of the parents and concatenate the, like, for example, concatenate the left side of the this blue data set and the right side of this yellow data set, and then produce the offspring. So there are like 8 offspring being produced. And the last step is the mutation. So the mutation is trying to still persist the gene diversity. So we want to keep that. So we are selecting some elements from those data sets and we are doing the gene mutation. So that's trying to replace the element from the original distribution of this feature. And then that's one iteration. So next one, we will go through these 4 steps again, like fitness evaluation and selection and crossover and the mutation. We will go through it until a predefined number of iteration has been reached. And then we will give we will select the fittest data set as the generated unfair data set. We have tested this modified genetic algorithm on 3 different kinds of unfairness matrix. The first one is calibration equality. So this one means that people in different group with the same number, like with the same predicted probability actually have same possibility of being positive. One violation case would be like 1 female student and 1 male student. They all have 0.2 predicted probability, but one of them is positive and one of them are negative. So this violates the calibration equality. The next one is overall accuracy equality. That means people in different groups, they actually have same accuracy. The third one is statistical parity. So this one is achieved when different group of people, they have same probability of being positive. And we also apply this modified genetic algorithm to different data set. One is simulated data set. So for the simulated data set, we have 2 different data sets. One is all features are continuous features. And another one, they include continuous features and binary features and also categorical features. Except for those simulated data sets, we also apply it to existing like real world data sets. For example, the MESIA data set. This one is we are trying to predict whether students are gaming the system based on their aggregated action information and also demographic features. Another one is student performance data set. This one is trying to predict students' performance given their demographic features. So now I'm showing the results of this of the modified genetic algorithm. So among all 4 data set and 3 fairness definitions, the average score of the unfairness is 0.08. And our generated data sets, the average unfairness score is 0.204. We are able to increase the unfairness for 0.125. And as you can see, the AUC score and the accuracy score, they still they are roughly same. And we want to say if the model learned on the generated data sets are still capture the relationship between feature and the label in original dataset. So we applied the model learned from those generated datasets to the original dataset. And we found that the AOC score are still pretty high and still similar to the model learned on the original dataset. And we also find that we only change about 3.6% of the entire dataset, and we are able to induce 0.12, improve the 0.125 unfairness. For next question, we are caring about the generalizability of this modified genetic algorithm. So we are trying to apply it to different kinds of problems. The first one is we apply to different number of data sets with different number of examples and different type of difficulties. This is achieved by using tuning the hyperparameter of the simulated data set function, the flip ratio. And also we want to say whether we can generate unfair data set for different classifier used in fairness evaluation. We have tried logistic regression, random forest, and extremely randomized trees. So here is the results. We are able to see that as the number of example increase, the time needed to generate unfair data set, it also increased. And also we found that with more number of examples, the unfairness increment actually decreased. And regarding the flip ratio, a higher number means that the problems is getting harder. So we found that it generally take similar time to generate the unfair data set. And the unfairness increments are roughly same for harder problems and easy problems. And also when we are trying those varying the classifier in fairness function, we find that if we are using the model other than the one used in fairness function to evaluate the unfairness of the generated data set, if we are using a random forest to evaluate the unfairness, but this one is evaluate the classifier in the fairness function is logistic regression, it does not show that much of improvement of the unfairness. And these trends are consistent for the other models. So if we are using a model to evaluate the unfairness, we need to use it in the fairness function. So for the last one is how does existing debiasing methods perform on those generated unfairness benchmarks. So we have tried reweighting methods, disparate impact remover, and equalized odds. So for the calibration equality, we can see that all of the methods they does not decrease the unfairness very much, and equalized odds would even increase the unfairness. Also for the overall accuracy equality, it still show the same trends. And for the statistical equality, we can see that reweighting methods and equalized odds are able to decrease the unfairness a lot, but not for disparate impact remover. So after we tested on those methods on different generated unfair data set, we are able to see that how it performs under different unfairness conditions. So we are able to get a more comprehensive understanding of those debiasing methods. So that's all for this studies. So the main takeaways of this work, including the first genetic algorithm can be modified to induce bias while still preserving the relationship between features and outcomes in the dataset from educational domains. Second, the generated dataset may not express unfairness in classifier other than the one used to measure fitness. And the last one is existing evaluation methods for debiasing methods may not accurately quantify the performance if keep using a small number of benchmarks. Because all of the, like most of the existing debiasing methods are trying to claim that they're able to decrease unfairness to some extent. But that's not enough. We need to like get a more like deep understanding of how they can do. So thank you all for your attention and listening. That's all for this study. Any questions?
Elon, thanks for that presentation. I'm wondering if you could, this is a bit more of a technical presentation as it was a LAK paper. I'm wondering if you could distill this down a bit and say, what is your biggest piece of advice from the work that you all have done on this? What's your biggest piece of advice for practitioners in this space?
Um, um, I would say this is more like trying to generate benchmark data sets for debiasing methods. So if people develop some debiasing methods, they can apply their methods toward like to different kinds of unfairness data sets. Like those data sets can generate it given different definitions. So they can like apply their methods to like broad uh, a broad benchmark data set, I would say.
Thank you. Any other questions, folks? We have a couple minutes left in this chunk of content here. You just blew all our minds. Just don't even know where to go with this. So, all right.
Yeah, I
Seeing,
guess yeah. Oh yeah, I just want to say I guess it's too more like technical focus. Maybe like people are more caring about if it can have some implication on more like learning analytic stuff, maybe.
very important. The academic research helps us as practitioners, and vice versa, hopefully feeds back. So thank you so much for your presentation.